No. Thank you. Just a second, yes. Can you start from the opening slide, please? Review and multimodal data fusion approaches.
So, can you hear me on the online?
Yes. Yes, no problem.
Thank you. Today I'm going to review some multimodal treatment approaches. So, if you know that every imaging modality provides unique and filtered and interrelated information of brain structural and functional organization. So if we combine the modalities, it can help to provide a more complete understanding of human brain and its disorder compared to unimodal studies. Because it provides joint or complementary information between them. After using the multimodal information, it increases the model performance. This is true not only for new imaging data but also for other domains. So, but how can we combine them? Because the challenging issue is huge amounts of data with characteristics of high volume and high variety and high velocity and also high veracity are generated due to the deployments of heterogeneous networks. And this data also referred to as multimodal big data, and which contains abundant intermodality and cross-modality information. And this present vast challenges on traditional data fusion methods. So I am going to present some deep learning models which are already used to fuse this multimodal big data, specifically some representative architectures that are widely used. We summarized here. So from today's presentation, I am going to present these three papers. So one is a short survey on deep learning for multimodal integration, application, future challenges, and then the survey on deep learning for multimodal data. And finally, is a new method, ImageBind on embedding system bind mode. So really, from the first paper, though the title is attractive, but I did not get so much useful information from this. So in the past, they provide this figure which demonstrates the concept of multimodal. We know that the world indeed is inherently multimodal, and we really depend on multiple senses capture information. In our day-to-day learning experience, we use all of the 5 senses to get data. Later, to use this data to make decision from this. So they give an example. I mean, some senses like sound and visual, touch, and interaction with human, and the human can understand that this is the object, this type of object. Here they use the dog as an example. And then they introduce the definition of multimodality as 2-dimensional concept. Like in the first dimension, that based on the taxonomical definitions of multimodality, they categorized as representation, translation, alignment, fusion, and co-learning. In the representation part, the needs of representing and summarizing in proper way the input features, and then the translation needs to translate one modality to another, and in alignment need to identify the direct relationship between one or more sub-element parts of the same input data. And then the future is the need of joining information in two or more modalities. And the for-learning categorized as follows. Details the need of transferring knowledge between modalities used in the experimental settings. And then in the second dimension, they divided into early fusion, hybrid fusion, and late fusion. So the early fusions happens when the multimodal input data is fused due to the application of the AI model. And in the late fusion, the fusion is takes place after the application of the AI algorithm. And in the hybrid fusions takes place when the multiple input data is fused both before and after the applications of the relevant AI algorithm. And they also divide into 5 categories, which is considered as subtypes of the 3 fusion, like early fusion, hybrid fusion, and late fusions. They categorize as data level fusions, decision level fusions, score level fusions, and hybrid level fusions, and finally model level fusions. And go to the second slide. So, and they described 4 applications of multimodality to deep learning, such as multimodal speech recognition, forensic multiple applications, and sentiment prediction, then multimodal image reconstruction or segmentations. Finally, they summarized some paper related to these 4 applications in the table. The second paper, I found some useful information from here, and this gives some future direction also. Now I am going to present this paper, the survey on deep learning for multimodal data fusions. At first, I am going to review some representative deep learning architectures. They are grouped into 4 categories. Such as embedding and step autoencoder, CNN, and finally RNN. We have to know that RBM is the basic block of the net, and it consists of visible layer and the hidden layer. The RBM it has fully connection from the hidden layer, from the units of the hidden layer to the visible layer, but no connection of units in the same layer. And the RBM, it uses the energy function to capture the probability distribution between the visible unit and the hidden unit in the following forms, and with the normalizing function Z calculated as this expression where X is the visible unit here and X represents the hidden unit, and the E is the energy function, which is defined by these expressions where W denotes the OS and C and B denotes the RBM biases. The visible and hidden marginal distribution of the RBM can be computed using this expression. So if we know that the deviant is constructed by stacking several RBM, it is based on a pre-training and fine-tuning training strategy. In pre-training, each hidden layer is greatly modeled as an RBM trained in an unsupervised strategy. After that, each hidden layer is further trained by the discriminative information of training results in the supervised strategy. a deviant with hidden layers represent the complex relationships in the following from where X is the input, zero the input objects, and probability of is L1 and given ACL represent the functional distribution of the L RBM that is composed of L-1 and L layer in the deviant. Here the conditional distribution is used to extract the directed high-level representation and the joint distribution to learn the undirected associative memory. To achieve the joint and conditional distribution in this architecture, each hidden layer is modeled as RBM and the output of lower RBM is inputted to the next RBM. So this process is repeated until the final hidden layer is trained. Then I'm going to talk about the step autoencoder. You know that the step autoencoder is a typical deep learning model of the encoder-decoder architectures, and encoder runs two functions, an encoding functions and the decoding functions. The encoding function that transfers the input data and the decoding function that degrades the input data from the encoded representation.
Ibrahim, just a quick interruption. Is it an old paper that you're covering, or like how old is it? So just because of the deep learning time scale, these approaches are so ancient. 10 years old.
Yeah.
Not so ancient for regular people, but deep learning has moved on. So I wonder.
Yeah, I try to take all of them, but yeah.
No, it's cool. I don't think everyone is familiar with this. So I'm just asking, is it an old paper or a newer paper? Like because I haven't heard this method's used recently.
Yeah, it's in 2020.
Interesting.
2020.
10 years old is an ancient now. Yeah.
But they are actually in this paper they first discuss about the representative architecture, and then they discuss the multimodal function model.
Yeah, go ahead. Sorry.
So they describe about the step autoencoder, and okay, I try to skip some part from here. This figure, this is the graphical model of the autoencoder, basic autoencoder, and step autoencoder. And there are some questions. This how they model, how the autoencoder is modeled. That is the let's say the given data X1 expression, the basic autoencoder input the raw signal into the compact representation and the hidden layer using this expression, and also the decode the intermediate representation using this expression where Y is the division, W is the Y, and B represent the bias, it is the nonlinear functions, and then optimize the parameter using this error function. Then they describe the convolutional neural networks. We know that it includes the fully connected neural network and the constant network, and it considers the local topology of the data, which was not considered in the deviant and the step autoencoder. Then they describe how the model, the input data, and also the optimization strategy using CNN. Then they talk about the RNN architecture. We know that is not only maps the input pattern to the output result, but also transfers the hidden state to the output by employing the connection between the hidden units. So in forward pass computing, RNN takes both the input and hidden state. In back propagation computing, it uses back propagation for time algorithm to back propagate the loss for the time direction. They demonstrate the RNN using this graph, and then that means if we have a training object on the level, then the mapping of the RNN is as the following expression. We didn't know about this one, so that's why I'm skipping this. Then they summarize some of the existing multimodal data fusion deep learning model and summarize the tables. So I am going through with some of them. So this is the MTBN, which is called Multimodal Deep Net. In this method, two modality-specific models are used to transfer the raw level and high dimensional image and text into the corresponding high abstract representation. Where each modality is with a defined statistical distribution. And then finally, they use one layer RBM to capture the joint representation by feeding the concatenated vector of each learned representation in the following form. And then there is another method. It's called DMTBN, Diagnosis Multimodal Deep Network, and this model diagnosing Alzheimer's disease, and there ADBN is used to run the deep representation of this modality by comparing the domain specific representation to the hierarchical abstract. Then one layer RBM is built on the concatenated vector, that is the linear combination of the hierarchical abstract representation from each modality. Then it is used to run the multimodal representation by constructing the joint distribution over the different multimodal features. Also, they use some other methods like HPDBN, human post deep net. This model estimate human post from multi-source information. They use the two-layer RBM to extract two-layer features from three features of the pictorial structure of human model. Then an RBM model that joint distribution over the multimodal. Another method is hybrid multimodal deep net that detecting sequential events with discriminative labels. And the conditional RBM is adopted to extract the intermodality and cross-modality features with additional discriminative level information. And then another the phase multimodal deep net that's recognizing faces from local and deep features. Local features of faces are modeled by the Cartlet transform, and the DBN is built on the local feature to run the deep features. In the stack ordering encoder architecture, from the stack ordering encoder architectures, the multimodal stack ordering encoder is the most representative multimodal deep learning fusion. So this model is to address two fusion problems like the cross modality and the shared modality learning representation. So they introduce three learning scenario. The first is multiple modality and cross modality and shared modality learning. Furthermore, in each scenario, to learn effectively, its first coding is used to realizing the loss function with the first constants of the following form. So in multimodal modality learning scenario, they train a RBM over the concatenated audio and video data. But since the correlation between the audio and video data are highly nonlinear, it is hard for a RBM to learn these correlations and from multimodal representations. So motivated by this method, then they implement bimodal deep unit network model, which is trained in a greedy layer-wise fashion over the pre-trained layer for each modality. By representing the data through learn fast layer representation, it's easier for the model to learn high order correlations across modalities. In case for cross modality learning scenario, first consider the cross modality learning settings where both modalities are present during teacher learning, but only one of them is keyed into the model in the supervised learning and testing. Then the deep encoder autoencoder is trained to reconstruct the both modalities, where the given only video data does discover correlation across the modality. But in this approach, the problem is since they use only one modality in the supervised training and testing, it does not capture cross-modality, complete cross-modality information. So then they proposed in the shared modality representation, a modality specific deep stack multimodal autoencoder is introduced to explore the joint representation between modalities, especially when one modality is sent. And then the training data set that is enlarged by replacing one of the modalities with zero is feed into the model in the future learning. And using this model, they represent that some result which perform better than the previous one, because it can capture cross modality information and also the shared modality information. There are other multimodal model like GIS and SAE generating human skeleton from a series of images. And in this case, the 2D image and 3D photos are transferred in the high-level skeleton space. Then the joint distributions are modeled by the MSC loss based on step autoencoder. And the other one is multimodal variational autoencoder detecting fake news, uses variational autoencoder architecture to learn the intrinsic distribution of our modalities with detecting loss from the detector. And another one is association gating mechanism, multimodal stack autoencoder, learning intrinsic features of words. And they use the multimodal encoder and decoder architectures to model intrinsic features of words with the association and gating mechanism. So, in DBN based and the autoencoder based method, They are fully connected neural networks. So the trains great numbers of connections because they are fully connected neural networks, so that produce great number of connections. So the train, the OS with this connection, it requires a great number of training objects to avoid underfitting and overfitting, and also it does not consider the local information of the features contained between neurons. So in the convolutional neural network multimodal fusion models, they use the local multimodal features using local field and the pooling operation. And also it is not the fully connected neural networks. So it reduces the number of connections. Here describe about the multimodal convolutional neural network in simple MCNN, and this one exploring the image sentence mapping at different levels. They use the one-dimensional convolution to capture the image sentence mapping at word, phrase, sentence level, that taking local topologies into consideration. And another one is AMCNN, called the auxiliary multimodal convolution neural network, that recognizing objects based on label and unannotated text. This network is composed of the language submodel and the visual submodel. The language submodel transfer text information into a dense representation of the semantic space. Then visual submodel captures the visual information. And another one is AVDCN, the audio visual deconvolution neural networks. It enhances speech signal with auxiliary visual signal. Here CNN is used to capture intermodality features in audio and visual signals. Then a fully connected network models the joint distribution by reconstructing the raw inputs. And another one is multimodal fuzzy convolution neural network, understanding emotion of video clips. And they use the fuzzy logic combined with CNN, used to model intermodality features from audio, visual, and text modality. Then they use some methods on recurrent neural networks. The first one is multimodal recurrent neural network method that generate a novel description of for images. It learns a joint distribution over the semantic space based on the given words and image. When an image comes, it generates a sentence word by word based on the captured joint distribution. In this method, it consists of a language subnetwork, a vision subnetwork, and a multimodal subnetwork. So the language subnetwork composed of a two-layer word emitting part that captures as effective task specific representation, a brain emitting one, emitting two, and a one-layer recurrent neural part that models the temporal dependency of the sentence. And the vision subnetwork encode the high-dimensional image into a compact representation. The multimodal subnetwork is a hidden network that models the joint semantic distribution over the learned language and the visual representation. They also review some other methods like MBI-RNN, multimodal bidirectional RNN, which generate this description for image at a glance, and also MTRNN, multimodal transform RNN, that labeling indoor scene from RGB and TIFF data and launched the multimodal joint distribution over the various modalities by the RNN and transformer layers. Then the multimodal gauging RNN predicting diverse behavior with low quality data uses the gate current cell with the multimodal sensor data to model diverse behavior. And finally, they describe the ASMRNN model. This one detecting ambulatory sleep from the wearable device data, and it adopts bidirectional LSTM to temporal features of the each model, and followed by fully connected layer that concatenate temporal features. So the RNN-based models are able to analyze temporal dependency in the multimodal data. But it is difficult to implement to parallelize in a high performance device. So in this paper, they summarize several multimodal data fusion deep learning models in 4 groups like BBN, SAE, CNN, and RNN. These models have made some progress, but most of the existing model first uses a deep model to capture private features from each modality. And transforming modality specific raw representation into high abstraction representation in a certain global space. Then the abstract representations is converted, is concatenated into a vector that represent global representation of the multimodal. After that, they use a deep learning model to model the joint distribution on the from the concatenate vector. So by using this method, they still now they cannot, that is this method is unable to capture complex semantic knowledge and also the cross modality information. And also the data, we know that data are collected from dynamic environments. So data are uncertain. So there are still have challenging issue to combine the multimodal information. So based on these challenging issues, and this paper proposed some future research possibilities of deep learning on the future learning of multimodal data, are to design new learning framework with more powerful computing architectures and combine the current compression strategy to design new compression methods of multimodal deep learning. Also combine of deep learning and semantic fusion strategy may be a way to solve the challenges posed by the exploration of multimodal data, especially for cross and intermodality representation. And then they also propose to design of online and incremental multimodal deep learning models for data fusion. And also they propose to address a deep learning model for low quality multimodal data. Now I'm going to talk about the new method for image bind. The one embedding space to bind them all. This is an approach to learn a joint embedding across 6 different modalities like image, text, audio, depth, thermal, and IMU data. The binding property of images offers many sources of supervision to learn visual features by aligning them with any of the sensory experiences associated with the images. But it requires acquiring all types of combinations of peer data with the same set of images, which is infeasible in practical. So we propose the image bind. It learns a single shared representation space by leveraging multiple types of image peer data, and it doesn't need data set where all modalities each other. It leverages the binding property of the images, just aligning each modalities, embedding to image embedding, leads to an emergent alignment across all of the modalities. It leverages wide scale peer data, image and text, and combines it with naturally occurring peer data such as the video and audio, image, depth, etc., to learn a single joint embedding space. And it also enabling the zero-shot recognition capabilities, which can be initialized with large-scale vision language models sort of three. For image binding modalities, they use the pair of modality for this termed as IM, where I represent the images in another modality to run a single joint embedding. And they use the largest wide data set with image text pairing that span a wide range of semantic concepts. And additionally, they use the natural and self-supervised pairing of other modalities like audio, tape, thermal, and IMU with images. Consider the pair of modality IM with aligned observations. So if the given image I and its corresponding observation in the other modality A, we input them into normalized embedding using this expression. M and G are deep networks, yeah. And then the embedding and encoders are optimized using info and CLO function, where tau is the scalar temperature that controls the smoothness of the softmax distribution, and J denotes the unrelated observations of all the negatives here. And the loss makes the embedding Q and K closer in the joint embedding space, and thus align I and E. In practice, they use the symmetric loss. So in their method, they termed as emergence alignment for the unseen pair of modality. In ImageBind, they use the image modality pairs denoted as IM, where I is image. Then it pairs with other modalities like text, video. They observe an emergent behavior in the embedding space that aligns two pairs of modalities. That means if they align the two pair of modalities M1, M2, even though we only train using the pairs IM1 and IM2. If the train IM1 and IM2, then the image bind provide emergent behavior in the embedding space like M1 and M2. This allows us to perform a wide variety of zero-shot and cross-modal retrieval tasks without training for them. Like they demonstrate image bind using this figure. We know that different modalities occur naturally aligned in different data sources. Like, for example, the image and text, and also video and audio in the web data, and depth of thermal information with images. So they represent the modality pair using this figure, like here the solid line represents the naturally aligned and the dashed line represents the emergent alignment. Let's say the image which is take the pair with like the depth image and video, text, and also video is aligned with the audio in the web data. So this the image binds links all of these modalities in a phone embedding space and the enabling new emergent alignment and the capabilities. In implementation to input the modalities, they use a transformer architecture, the vision transformer, VIT for all of the modality encoders. For encoding audio, they convert it into a spectrogram. As the spectrogram is also producing like an image, they use the VIT to encode it, and then it treats the thermal image and depth image as one channel images, and also use vision transformer to encode them. And MU reading are projected using a 1D convolution with a kernel size of 8 and the encoded using a transformer. Finally, they follow the text encoder designed from T. Use separate encoder for image, text, audio, thermal images, depth images, and animation. Then added a modality specific linear projection and on each encoder to obtain fixed type D-dimensional embedding. This model, they use several data sets like audio set, sound RGBD, LSBIT, and Ego Korean large scale data set. From this data set, they take the pair, modality pair, like from audio set data set, they take the video and audio pair and the sound RGBD that is image depth. And LSBIT data set, image form, Ego for the data set, video and large scale data set, they take the image and text. They give a new term here, the emergence zero shot and the zero shot like in the clip, the method, the clip, they use the pair image and text pair, and the audio clip, they use the audio and text pair, but in image bind, they take the image and text and image audio, not directly use the audio text. But it can also generalize for this pair. So the term as emergent zero shot classification. The image bind outperforms in their experiment. Actually, they show that their method outperforms pure method on zero shot criticals and has comparable performance in the classification task. And also they evaluate the level efficiency of image bind by evaluating on the future classification. They use the audio and text encoder from the image bind and evaluate them on audio and text classification respectively. In this case, both these lines use the same capacity and AGB audio encoder as image bind. They train linear classifier on fixed features for the few-shot case. In the left side, all setting the image bind, the sheet show that the image bind outperforms the self-supervised audio MAE models, and also even it performs better a supervised audio MAE model after 4 shot learning. In the right figure, they compare with the multi-MAE model trained with images, depth, and semantic segmentation mask, and image bind outperform multi-MAE across all feature settings on feature depth classification. also experiment that embedding can be used to compose information across modalities. Also without retraining, they can upgrade existing vision model that use the image embedding from other modalities such as audio. Here in the left figure, they add image and audio embedding and use them for image retrieval. The composed embedding naturally captures semantics from different modalities. For example, here, here they use an image of fruits and the sound of the birds that can retrieve image of birds and surrounded by fruits. And also they also evaluate the model by replacing the clip-based class embedding with their audio embedding lead. That audio embeddings that lead to an object detector with audio. And in this case, no need to retain of this model. This figure demonstrates that their model enables cross-modal retrieval and also is adding embedding from different modalities, naturally composes their semantics and like embedding space arithmetics like with the image and the sound. Then they generate the image like which naturally composes their senses, and also the audio to image generation by using their audio embedding retained to decoder designed to work with clip text embeddings. So the main point of this method is that that means the previous method for the multimodal fusion, they need to train all of the pairs, but in this method, the change some no need all of the pairs like they use only some the naturally aligned pairs like they take the image according to the model, they take the image, I mean the pair of modalities equal to the IM, they take the image, then with the image, they take the another modality like text, audio, and video. And then train with this pair, and this model can generalize for other pairs, which is not seen during the training. Okay, this was my presentation. If you have any questions about this.
Yeah, thanks. So you went like from the beginning, like the early approaches, the multimodal fusion, and you actually went to clip, and what was the investment? Like, this is one of the very early paper. I don't remember even when it was published, 2013 or something like this multimodal approach, like this picture. The figures, I think it's by Salakudina, but all like his team. So what are you looking for? And then you didn't get into transformers that much, maybe in those approaches, right? when you were describing the models, you didn't cover transformers. Do you know why? Like you paid special attention to RBMs, deep belief networks, RNNs, but SCNNs, but not transformers.
No,
Or
they don't describe about the transformer here.
Otherwise, well, transformers were in like when you start talking about clip and everything, right?
Yeah, that was the, not this one, that was the
No, okay.
ImageBind another paper.
Yeah, ImageBind.
This one is the new paper.
Yeah, but you didn't cover like transformers as a separate model, that's why, like, because you covered the rest. So are you trying to apply it to brain imaging?
Yes, this one. But I don't know how, maybe it's used for that.
Oh, okay, well, wouldn't it, like, do you have ideas? Because I'm thinking like, if the model could verbally explain itself. Like, my prediction is because amygdala is blah, 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 or like, there is a lesion in the area of that region. Or like, things like that, so connecting text.
Yes, that means one reason is connected with other, like,
Well, text, right? So your multimodality is still text, it's the same. Or you type a description and it finds you an image by description. Like say, oh, find me images that are flipped upside down in this data set or something like that. Can we do that? So, because we have like for quality control or for specification of like find me that region and it does segment that region for you. Or for another third case is interpretability, but reverse. The model is generating text from the image, not just showing you like hotspots like we're looking, but telling categories. It's like this is an explanation. See, imagine we take fax archive from the doctors and take an image, MR image, T1 or something, and the doctor conclusion and train it on it. And then we give it a new MRI. Can it generate a conclusion what's wrong or nothing is wrong based on that MRI? That will be one of the approaches, right? But you probably want to combine imaging modalities, not text.
It'd be hard to find a unified data set, right, kind of stuff, right? So it's gonna be,
But
you're gonna get all sorts of text, right, related to images, and you're gonna be saying such different things, right? What would you be potentially predicting, right? So you want to, if you want a general model that can do these things like find me a region, if you don't have any text where, a doctor is saying anything about specific regions of the brain, that model's not gonna be able to do that. Right.
well, that's how we started with those models online. People write all sort of
Just baloney.
yeah. It was trying to censor.
And one thing,
But still it works. Yeah.
here is in the ImageBind, okay, for the data, image, video, and text, the audio, find the text, and the text appear like the image and text and image and video. So that means that are naturally aligned.
Well,
We
naturally,
can understand easily, but how can you take this such type of pair in case for?
well, I told you to.
Subcortical or other, in subcortical also there are some component. How can I add?
We do that when we talk to each other, right? When we discuss those things, or when doctors write notes, aligned or attached to the imaging. There is some information about the imaging if they're describing an MRI.
Problem is, so the way I think about like how a doctor works, right, is so they're not only sort of looking at the image and generating text, they're also drawing on training, right, and years of biological context and experience.
Let's read it out from that text. Let's learn.
And so you would need a doctor to provide all their life experience and training and.
As a little prompt to generate. Yeah, thank you, Ibrahim. I'm stopping the record. Thanks everyone for watching.